So here's section 4.0, theorem 4.0.3. Now this is a big time theorem. They give us no proof. It's actually kind of a mess. I looked at this myself, and it's there are various ways to get at this, and I don't. It's just kind of interesting that they put this theorem right here, and no proof, but they don't even talk about the fact that they don't give a proof. They just state the theorem. So let's get to the theorem. We can get the determinant of a matrix by expanding not just on row 1, we can use any row. And so if we change our definition where we could use an I instead of just row 1, so then this would be Aij instead of A1j, and then the minor ij instead of A, then this is for any I. So that's the expanding about any row, and then similarly you get the same answer if you expand about any column. So we change this to I equal 1 to n, -1, and we can still use I plus j, and we can still say Aij. We're just going to march down. Notice we're summing over the i's, so it's going to be for any given j, which is a column, and then Mij of A, and this is for any j. Okay, so what this means is if I have a matrix that's a little more sparse or something like that, say this is 2, 3, -5, but the middle row here is 0, 1, 0, something like that, and then 4, 8, 7. Then what I'll probably want to do is use that row for my determinant, and so the determinant of A is equal to, I take -1, and this is to the, this is, I start with row 2, column 1, so that's 2 plus 1, and then times the 0. Now the nice part is, that's just, we just get, for our Aij, we just get 0, and that's why I'm choosing that one. So 0 times the minor of 2, 1, and then plus -1 to the 2 plus 2 times 1, and then times that minor of 2, 2, and then plus -1 to the 2 plus 3, because I'm in row 2, column 3, 0, and then M 2, 3. And so, of course, those I don't even have to calculate. And so my determinant of A is -1 to the 4th times 1 times my minor 2, 2. So that's going to be the determinant of 2, 4, -5, and 7. And so this, I get a 1 there, 1 there, and so I just get 14 plus 20, or 34. So much easier than trying to expand by the first row. Okay. Similarly, with the first column, or with any column, if we had A was equal to you know, 4, 8, -6, and again, you know, 0 to 0, something like that. And then, you know, -5, 4, and 3. You know, once again, the idea would be, oh, I'll expand by that column. So the determinant of A is equal to -1. Okay, that first 0 is in row 1, column 2, and then times the 0, and then the minor of 1, 2, plus -1 to the 2 plus 2, because I'm in row 2, column 2, times 2, and then times that minor of 2, 2, and plus -1 to the 3 plus 2 times 0, times the minor 3, 2. And so once again, because those are zeros, that's quick and easy to calculate. And so I get 1 times 2 times the determinant of 4, -6, -5, and 3. And so that's 2 times 12, minus 30, which is -18, so we get -36 for this determinant. Okay, so that's theorem 4.0.3, and you know, and how we can use it in a practical way to help us calculate a determinant for something that maybe has a lot of zeros in it. We can exploit those zeros by choosing any particular row or column. Okay, so we can do it any way we want.